Hello everyone, and welcome to Objective 2 for day 26. This is the third podcast for this day. In this podcast, we're going to talk about how genetic drift and gene flow can affect the frequencies in a population. We've already talked a little bit about genetic drift and gene flow, but we're going to talk a little bit more in detail here. So to remind you what the definition of genetic drift is, let's write that here. And remember, genetic drift is defined as chance events that cause allele frequency to change. Genetic drift has a greater impact on smaller populations. So let's write that here. Greater impact on smaller populations. And the reason for this is because a smaller population has a smaller gene pool. Your book uses an example of an area in the woods that has various flowers in it. And so I'm just going to draw circles here. So we have blue flowers, we have green flowers, we have red flowers, and we have black flowers. Fairly well distributed. But maybe walking across this population of these flowers, remember it's a population, so it's a single species, but we have variety here. And let's say walking across here, a moose of some sort, say, walks right across here, and as it's walking, it eliminates all of these because it stomps on those flowers. And as you can see now, what has happened is we used to have a fairly well equally distributed population here, but what's happened is we've reduced the allele pairs in this population because the moose walked right through here. Now, the moose didn't specifically look for blue flowers or red flowers or green flowers or black flowers. It didn't care. It just walked. So it was a chance event that he or she happened to walk right through here. And now you can see we have 2 blue, 1 green, 1 red, and 3 black flowers. We've changed the distribution, the frequency of the alleles in this population due to a chance event. It's important to remember this kind of take-home point from this here is that genetic drift will always have, so let's say has significant impact on population. And there are 2 examples of this that we're going to talk about. The first is the founder effect. The second is called the bottleneck effect. So we're going to spend some time talking about these 2 examples of genetic drift. So let's talk about the founder effect first. So the founder effect is when you have a few individuals who get isolated from a larger population. This new, smaller group forms a new population. This new population now has a much smaller gene pool. Alright, I'm going to give 2 examples here of the founder effect. One is an example of what might happen, well, let me just draw it here. And let's say we have some large landmass here, maybe a continent. And this continent, maybe there's all kinds of a particular bug, an insect of some sort. Let's call them ladybugs. We can call them whatever we want. So we have a fairly well diverse population here of ladybugs. Well, the founder effect says that somehow or another a group of these, a small group of these, are going to get separated from this large population here and end up in a new area. And let's just draw an island here. So you might have a situation where maybe these ladybugs get attached to a bird that could fly to the island. Maybe they get washed away, maybe they get blown away. However it happens, let's just say these 3 individuals here get taken away and they end up on the island. How they get there is really not as important. The fact that they get there is what's important, and that they're separated from the larger community. And as you can see, what has happened here is that we have lost part of our diversity. We no longer have the red ladybugs here. As a result, this population, the smaller population, is going to begin to divide. And as they divide, we're only going to have green, blue, and black individuals. Other forces of natural selection could act on them as well, but right now we're just talking about how the founder effect establishes this new population here with less genetic diversity because only a few individuals are forming it. Alright, so let's talk about the disease called Huntington's disease as our next example. This is a disease that causes severe neurological problems and brain deterioration, but one of the features of it is that people don't experience symptoms until they're in their 40s or 50s. And because of that, they will already have had their children by then. And so people were interested in finding the gene that caused this. And one thing that we often do when we want to identify a gene is we look for small regions where that disease has a high frequency. So in this small region in Venezuela, there's an increased number of people with Huntington's disease. This was an ideal place to begin to look for the gene. And in the search of the disease gene, they made a very interesting finding, and they were able to trace this gene, this mutation, back to a single individual. Remember, another thing to point out again is that this is a very small community, so there's very little breeding that happens from the communities around it, okay? So it's very isolated. So once a mutation is in here, in this region, it pretty much is going to stay there for a long time. So they found, well, they didn't find the woman because she was dead, but they were able to trace it back to this one woman from 200 years ago who had Huntington's disease. One way to pass, as we've talked about before, is having this disproportional reproductive success. And that's what she did. She had 10 children. I forget off the top of my head how many of these children had Huntington's disease, but as I recall, it was greater than 5. So it was greater than 50% had it. It doesn't really matter how many had it. The fact of the matter is she had a bunch of children. A high percentage of those children had Huntington's disease. And because they were able to survive and reproduce before they had the disease started to show symptoms, they also passed it on. So over generations and many generations, what happened is from this one woman who had 10 children, she was able to pass it on into the small community over and over and over again. And so this is an example of a founder effect. This one woman, she was the founder of Huntington's disease in this region here. And from this region, it then began to spread to various other parts of the world. Next, I want to talk about the bottleneck effect. This is caused when there is a sudden change in the environment. That can drastically reduce the population. It's similar to what we just talked about, but let's say we had our population here, and let's draw some diversity here, and we'll just, again, we can say these are beetles like we have before. Well, let's make these trees. Let's make this a population of a specific tree. And of course, they're not necessarily these different colors. We're just using the colors to signify that there is diversity within this population. And let's say this diversity, let's just make it height. Maybe let's just call some of these things out here. So maybe a black tree, let's say it is the shortest. And let's say the blue one is the next shortest, and the green one is the next in the line, and then the red one is the tallest. Now let's say a forest fire comes through here and wipes out a large portion of this population. So now this is different than the founder effect, because the founder effect says a few of these individuals move away. Here we're saying there's a sudden change in this environment that drastically reduces the population and thus reduces the diversity. So let's say there's a forest fire here that wipes out all of this here. And now what you have left are just these few members left. 2 red and 2 blue. So we have 2 of the tallest variety and 2 of the almost the shortest variety. Now we can see how this has drastically reduced the variety in this population. Now what has to happen now is that these 4 have to begin a new population. And so we say they have passed through the bottleneck. Right? Think of your book has a good figure where they show if you flip over, if you fill a bottle with marbles or something like that, and you flip it over and let them fall out, only a few of them can come out at a time. Same thing here, only a few of these survive. So we say they have passed through this bottleneck and have survived. Now, we continue to see this problem in this population even as they begin to grow, because we have this reduced diversity, and we also have other things that have occurred because of it. Maybe the birds that live in these trees, now they're going to be affected. And we'll continue to have this problem until this population once again becomes much larger. Once they continue to divide and divide and divide. In fact, why don't we just show that? Say over time, maybe 100 years or so, maybe more, we see that these trees now begin to take over, and now the population is much larger. But what you'll notice, that even though the population has returned to the same numbers, the genetic variability is much lower now, because we lost such a large amount of trees in that sudden change to the environment, the forest fire. Your book has a pretty nice example talking about prairie chickens, and I want to show that to you real quick. So let's look at that. So let's first look at the overall story here. And what happened in the 1930s to the 1960s, we had a lot of these prairie chickens here in the state of Illinois. Had a very large range. The prairie chickens were over, roughly 75% of the state. And then what happened between, say, between the 1930s and 60s and all the way to the 1990s is that much of the prairies had been taken away, either turned into farmlands, turned into growing cities, roads formed, and all that. And as a result, only a few of the prairie chicken populations survived. In fact, what we see here, it says in 1993, with less than 1% of the grasslands remaining, the prairie chickens were found in just 2 locations. So they passed through that bottleneck. So now let's look at the data at the bottom of the picture. So let's look at the numbers now. We can see in the state of Illinois, where we saw this reduction of prairies and the reduction in prairie chickens, we can see that in the 1930s and 1960s, we had a fairly nice, robust population of 1,000 to 25,000 over that time period, and that the number of alleles in that population was 5.2. Percentage of eggs hatched was quite high, nearly 100% at 93%. Then we could see what happens in 1993 once all those prairies, or much of those prairies, have been eliminated. We see the population size plummeted to less than 50. That correlates well with the number of alleles, 3.7. And again, that correlates with this eggs being hatched. So scientists went around and counted the number of eggs they saw and the number that hatched. And we could see that is less than 50%. No wonder our population plummeted of the prairie chickens. One explanation is that with a reduced diversity of genes, a reduced size of the gene pool, that this population, this reduced population, had a tougher time surviving, not only because there was less prairie, but because of all other kinds of evolutionary forces that might act upon those individuals, which then in turn affects the evolution of the population. Now we can see in other areas where, say in Kansas in 1998 and Nebraska in 1998, we see very strong sized populations here, 750,000 to 75 to 200,000. And we see in these individuals that we have similar sizes of number of alleles as we did in Illinois in 1930s to 1960s. And we also see a similar percentage of eggs being hatched, 99% and 96%. This suggests strongly that having an increased number of alleles, increased genetic diversity within a population allows for a greater reproductive success. And of course that is what fitness is all about. These populations are much more fit than this population in Illinois, and it's correlated with the number of alleles. Alright, let's talk about this last topic called gene flow. We've discussed gene flow before, but let's bring it up again. Gene flow is the transfer of alleles into or out of a population due to a movement of fertile individuals. I'm going to talk about an example of the bighorn sheep. They were the same ones that we talked about when we talk about intrasexual selection. This study is more than 10 years old now, but it's a pretty good study, and there's similar ones out there as well. But the bighorn sheep were able to operate or survive in this very large population. And within this population, there was free movement of the bighorn sheep all around. So it's a large enough population where you might have had maybe different populations. And there would still be diversity within these populations. There might be, well, we'll just draw it like this. And it was able to maintain this diversity because of gene flow, at least partly because of gene flow. Because bighorn sheep in this population were free to move in this direction and mate with individuals in this population. Individuals went this way and back and forth, right? In all different directions. And we know it doesn't actually take a whole lot of movement between these different populations to get that increased genetic diversity. You only need a few moving over during each breeding season to see a pretty big impact. So what happened was, now as expansion occurred out west, we would all of a sudden start building in roads. So we might build a road through here. Maybe some highway. Maybe had a highway coming over here connecting with this road. Maybe there's a nice big road going this way. So all these roads here were made by humans because we like roads. We like roads, but bighorn sheep, they don't like roads. And so what happened now is that the bighorn sheep in this population did not go into this population, and vice versa, and these other examples as well. We saw a much reduced ability of these bighorn sheep to move between populations. either it was physically impossible to go across here, or they learned really quick that it was quite dangerous to cross these roads because of cars and other vehicles moving down them. So over time what happened was that this gene flow was blocked, and we could tell, much like we saw on the previous example, that the diversity within each of these populations, the genetic diversity in each of these populations, was blocked. And it was blocked because of a reduced gene flow. Remember, before the roads, these sheep could move in either direction and could mate with individuals in each population. Once the roads came in, it made it difficult, or in some cases impossible, for the sheep to mingle between the different populations. The end result is that we see a decline. I'm going to draw a down arrow here, a decline in genetic diversity. Over time, what's going to happen now is that since there's less genetic diversity here and here, just like we saw with the prairie chicken, these numbers are going to decline. Their overall numbers will decline because their gene pool is being reduced, because they're not having that influx of genes from their neighboring populations. Okay, that ends this podcast on Objective 2 for tomorrow's class. If you have any questions, please let us know. We'll be happy to answer any questions you may have. We'll see you in class. Bye.